Hello, Coach Travis here with another calculus video. So, alright, this question is asking us to evaluate a definite integral of this rather intimidating looking rational function here. Yikes. So it looks pretty scary, but I think if we don't get too intimidated, we'll be able to figure it out. So, all right, so let's see, what am I going to do here? So this is well, we're in the section on U substitution, and so I'm gonna try a substitution here. But then the question is, well, what are you going to set U equal to? It's kind of, you know, what's the inside function and what's the outside function? Or, well, actually, you don't even care what the outside function is, but what's the kind of innermost function, or what am I going to do here? That's what I'm trying to say. So when you're doing U substitution, it's often helpful to look for inside functions. Another thing that's also helpful to look for is functions whose derivatives sort of show up in other places. But at the end of the day, really, the best thing to do is just try something. And if it doesn't work, that's okay. You go back and you try something else. And there's no penalty. You know, how do I say? If you make a guess and the guess just doesn't seem to, if you get stuck, you know, like if you make a guess and you try to force it to work, well, then you're probably going to get the wrong answer because it was maybe a bad guess. But if you make a guess and it doesn't seem to be working, you can always go back and make another guess. So, but I've done these problems a lot, so my guess here is probably going to work. So I'm going to say U is equal to 2x squared minus x, and basically the bottom. And why did I do that? Well, one reason I did that was that if I think about inside and outside, if I think about inside functions and outside functions and composites of functions, then when I look at this function, the denominator is kind of more inside, because it's like the numerator of a fraction just gets to be in the numerator, whereas the denominator of a fraction, it's the one that's actually getting divided. It's the one that's actually getting reciprocaled, for lack of a better term. So I think that's a reasonable guess. And another reason why I made that choice for U was if I think about what the derivative of the denominator is. If I think about, in fact, maybe I'll write it down over here. Let's just figure it out right now, because we're going to need it. If I find the derivative of both sides of this with respect to x, then I get 4x minus 1. And 4x minus 1, you might say, well, what's the significance of that? Well, at first glance, there's no significance. But look at the numerator here real carefully. Is the numerator at all related to 4x minus 1? And I think if you stare at it long enough, you'll say, yeah, it is. What I've got here is I can say that 2 minus 8x is equal to, it's actually equal to a negative 2 times that 4x minus 1. So these guys, this guy and this guy, they're not the same, but they're close cousins, and that's important. So when you're doing, that was the idea there, that when you're doing U substitution, what you want to look for is you want to look for inside functions, and what you also want to look for are functions whose derivatives show up in other places in the function. That's kind of the secret to doing a good U substitution. But it is hard. If you're struggling with finding the right, if you're struggling with what to pick for U a lot of the time, that's totally understandable because it really takes a lot of practice. It's sort of an art in learning how to pick a good choice for U. So just keep practicing, and the more you practice, the more of a feel you'll get for it, and the better you'll get at it. So all right, so anyway, so let's keep going here. Where was I? Oh yeah, okay, so over here, I don't like this because it has U's and X's mixed together. Somehow I want to get rid of all the X's and have them be U's. But of course, it's not legal to just erase the X's and put U's there because X is not the same as U. So that's what we're going to use this scratch work over here on the side to do, is I'm going to multiply both sides of this equation by dx. So what I've got here now is I've got du is equal to 4x minus 1 multiplied by dx. And now what I can do is, using this little scratch work that we did up here, I could say, hey, why don't I got an idea. I think I'm going to multiply both sides of this equation by a -2. And if that's you might say, why the heck are you going to do that? Well, trust me, and let's see what happens. So if I multiply both sides of this equation by a -2, then what I get is, well, on the left-hand side, I get a -2 times a du, and on the right-hand side, what I get is I get 2 minus 8x multiplied by a dx. All right, do you believe that? Because, okay, what did I do? I took this equation and I multiplied both sides by a -2. I should have showed my work better there. So I multiplied both sides by a -2. And so on the left-hand side, it's just -2 times du. And on the right-hand side, well, -2 times -1 makes +2, and -2 times 4x makes -8x. So that's what I did there. And why did I? And why is that so darn helpful? Well, because look at what we got in this formula here. I'll highlight it. Here's a 2 minus an 8x, and here's a dx. Oh, and I should say that whenever you have a fraction, there are always invisible parentheses around the numerator and the denominator. So a lot of the time we don't write those parentheses, but part of the notational convention is that those parentheses are always assumed to be there. And so what we got here is, yeah, we've got this. This is my green stuff. Here's the green stuff, and here's the green stuff. Those are exactly the same thing. And so what that means is I can trade all of that green stuff, I can trade in for a -2 and a du. So all right, so now what we're going to have is we're going to have the integral of let's see. So when this goes away, it's going to turn into a 1. I mean, because you gotta have something in the numerator. So essentially, yeah, essentially what we're doing is we're dividing. You could think about we're dividing. No, wait, what are we doing here? In some sense, yeah, we're doing a division. And when you divide 2 minus 8x by 2 minus 8x, you get 1. And then you've got a u. And now the green stuff went away, and it turned into a -2 and a du. So we traded in the green stuff for a -2 and a du. And now you might say, wait, Travis, you forgot something. You forgot the 2 and the 1. And I did forget those, but I actually forgot them on purpose. Because I'm going to put question marks there. Because it's not correct to put a 2 and a 1 there. And the reason is that the 2 and the 1, those are x values. 1 and 2 are values for x, because they were part of the integral when we were integrating with respect to x. But now we've changed to integrating with respect to u. And so 1 and 2 are x values. They're not u values. So it would be wrong to put a 2 and a 1 there. You could take the time to figure out what we should put there, but I think it's easiest just not to worry about it. And at the very end of the problem, we'll back substitute and bring the x's back, and then we'll be able to bring the 1 and the 2 back. So I think the simplest thing to do is just leave the question marks there for now. Okay, so now what am I going to do here? Okay, well, the -2 is a constant. Oops. So I can factor it out. The -2 is a constant, and so we know that we can always factor constants out of integrals. And now we've got the integral of 1 over u du from question mark to question mark. Okay, and so now this is a definite integral, even though I don't know those limits. It's still a definite integral, because those are some numbers. I'm just lazy, or well, not lazy, but I haven't taken the time to figure out what those numbers are. So what I'm going to use here now is I'm going to use the fundamental theorem of calculus. So the fundamental theorem of calculus says that to evaluate a definite integral, what you have to do is you have to find an antiderivative. So what I have to do is I just have to find the antiderivative of 1 over u and then evaluate it at the upper and lower limits. And so let's see, can you think of an antiderivative of 1 over u? And you can pause the video and think about it if you want. Probably a good idea. But hopefully the thing you thought of was it's the natural log of the absolute value of u. That is, let's see, yeah, that's that the antiderivative of 1 over u is the natural log of absolute value of u. So that's one of those special antiderivative formulas that you've probably talked about in class already. So now at this point I'm stuck unless I can get rid of these question marks. And the way I'm going to get rid of those question marks is I'm going to back substitute. I'm going to bring x back into the picture. So if I think about what was u, u was just a placeholder for something more complicated. U was a placeholder for 2x squared minus x. So wherever I see a u, if I want to, it's perfectly okay to put 2x squared minus x. And now once the x's are back, then I can bring back the 1 and the 2. And so now we're almost done. Now we just have to plug in the 2 and plug in the 1. And so we wind up with -2 times the natural log of, okay, if I put 2 in there, I get 2 times 4 minus 2, and that makes 6. So I get natural log of 6, and then minus, if I plug 1 in there, I get 2 times 1 minus 1, which is equal to the natural log of absolute value of 1. So one thing we can see here is the absolute values actually aren't really that important because everything we're dealing with is positive. And now if you're sneaky, you'll see one more simplification we can make. So what's the natural log? Quick quiz. What's the natural log of 1? And the answer is 0. The natural log of 1 is a logarithm of any logarithm of 1 is 0. So, all right. So that means we got our final answer here. It's just going to be -2 times the natural log of 6.